begin the lecture, right? So we already talked about caching and how, I guess, magical, as in like somehow it make your program a lot faster. All right. Today we'll talk about more of the design issue that comes with caching. What are the basic things that you have to talk about in caching when you program, especially when you write your code and you want to make sure the code are fast, right? So let's do a quick recap from Thursday, right? Oh, sorry. So the basic caching recap. So when I have an address, let's say I have a pointer in C, int, oops, sorry, again, I need a pen. Int star I equals 10, right? What is I? What is the variable I here? It's a pointer. What does a pointer store? Does it store your data or does it store something else? It stores an address. Thank you. Perfect. This is your address, right? And with caching, what now that we have the address, to be able to check whether my data is the cache, what are the 3 pieces of information you are going to extract from the address? These are called tag, index, and the byte in block, right? And we will review this one by one because it's a weekend, right? It's been 5 days, and I'm pretty sure with all the class you've been taking so far, you might have forgotten that, right? Again, I was in your shoe before this thing does happen. So let's recap. You can have this thing called a cache block, right? Cache block has certain size. So let's assume it's 32 bytes long, right? Let's say our cache block is 32 bytes. This is going to be byte 0. What byte is this? The last byte in here. If I start with byte 0, I have 32 bytes. Wake up, guys. 31. Yes, thank you. 31, byte 31, right? Byte 31. And so let's say my address want to point to byte 17. What should be in the address? At the last bits of the address, what should be the number over there that I can make sure that I am going to point to byte 17 here? So let's say these are my address, right? This is my int I, right? This is I. It stored my address. I'm going to break this down into 3 chunks. So let's assume this is 16 bits, right? These will be your byte in block bit. This will be your index bit. So if I want to point to the byte 17 in my block, right? If I want to point to the byte 17 in my block, what's the easiest way I can do this? How do I tell that that's going to be address that point to byte 0? That's going to be address that point to byte 7. That's going to be address that point to byte 13. That's going to be address that point to byte 21. How do I do that? From your address. Can I just put the number 17 in here? Why not? Is that a yes or no? But if you say no, why not? Is it because you want, yeah, exactly, right? Do you want a binary number? So what's binary of 17? So can I put 10001, which basically translates to 17? Yes, right? So you can put 17 in here, as in like you can put 10001. So the byte in block bits will have the binary that correspond to the exact byte that you're trying to access. So let's say address of I, right? Int star I has the pointer pointing to byte 17. Well, int is 4 bytes, right? So in this case, you want byte 17, 18, 19, and 20. This is where I is pointing to, right? My pointer. The address is going to start at byte 17. So over here is going to be 10001. Then the instruction in assembly would tell you that's a load word for 4 bytes. Then the computer would know that, okay, I will start from 17. I'm going to get the next 4 bytes for you. All right. So that's a byte in block bits. Let's say I have 8 sets for my cache. I have 8 sets for my cache. The index bit tells me what set do I go to. So how many bits do I need for 8 sets? I just need to be able to represent set 0, set 1, set 2, set 3, set 4, set 5, set 6, set 7. So how many bits needed for that? So I have 8 sets. I need 3 bits, right? So let's say the index bit in this case, 3 bits. And in there, I have 0, 1, 1. What set do I go to? If the index bit is 0, 1, 1, what set do I go to? I'm going to go to set 3, right? If the index bit instead of 0, 1, 1, it's 1, 1, 0, and then I'm going to go to set number 6. So let's assume the index bit is 1, 1, 0, right? You can go to set number 6. And in here, let's say the tag is some binary A. The tag over here is B, tag is C, and the tag is D. Oh, yeah, sure. So there was a question why 8 sets correspond to 3 bits, right? So the point of having the cache set is to make sure that if I have the address, in this case, the int star I, right, is an address, I want to be able to pinpoint to that, hey, I have this address. It's going to be in one of the set. I can have this address going to set 0, set 1, set 2, set 3, blah, 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 up to set number 7. The set ID would correspond to the index bit I have in my address. The index bit would dictate, basically, it would dictate what set do you go to. So that's how caching works in hardware. So I have 8 different locations. I can represent the index bit using a binary number. I want to make sure, because I have 8 different sets, right? I have set 0 up to set 7. I want to make sure I can represent the number 0 to 7. How many bits do I need to be able to represent the number from 0 to 7? Okay, you got it. Basically, that's when you say, hey, I need 3 bits. It's just because in reality, you need to be able to represent the number up to 7. So you need 3 bits for that, because with 3 bits, you can go up to 111, and that'll be number 7. If I somehow have a weird cache that has, say, 14 sets, how many bits do I need for that? I can go up to set number 13, set 0 to set 13. Does 3-bit works, or do I have to go to 4 bits? Yeah, you have to go to 4 bits, right? Most of the time, the number of sets would go based on this 2 to the something, like 2 to the factor of something. I have seen some other different structure that would be kind of lovely to go to the 2 to the something, but it doesn't really like go to the up to 15. For example, there are certain elements of the GPU not related to the cache, but use these bits in the address, and then go to 0 to 5, right? So sometimes you would have to manage that differently. So in this case, you have, let's say you have 13 sets or 14 sets, you would need 4 bits because 3 bits is not enough. You need to add 1 more bit. So in a set, let's say you zoom into set number 6 in this case, right? In the set number 6 right now, there's 4 cache block. The first cache block has tag A. A is just some random binary. And it just happened that over here, the tag is C. Is that a cache hit? So the rest of your address is the tag, right? And the way you determine whether my data is in the cache or not, you compare the tag with what's in the cache set. In this case, is tag C in my cache? If you go to set number 6, can I find tag C somewhere here? Right. So in this case, it's a cache hit, right? It's a yes. The answer to that is a yes. So you can find the tag C in there. So it's a cache hit. What if your tag is something else? Your tag is E. In this case, what would happen? It's a cache miss, right? Your data is not in the cache. You would say, hey, I want to search for my tag. Well, it's not there. So where do you go to get your data? Next level of the cache or DRAM, depending on where you are, right? You go to the bigger storage and say, hey, is my address here, right? So this is how caching works. The second thing we talk about on Thursday is called the set associativity, which kind of have something to do with what we want to talk about today as well. So that's why we do a recap. The concept behind set associativity is to hopefully address the direct map cache problem. Direct map cache is every single set has one cache block. If I have new access to the set, I kick the old thing out. Set associativity basically means that you have n cache block per set. The way you implement this is there are multiple cache blocks in a set. Oh, okay, great question. So the question is, does the address usually be 16-bit? Nope. Depending on the architecture, these days you're looking at close to 64 bits, right? Because if you have a 64-bit architecture, you can go up to 64 bits. Right now, the Intel manual, so let's say you have an Intel chip, I think it go up to 52 bits or 40. I forgot about that, but it go like something in the 50 something bits. Does it answer your question? Because I have another question on the chat right now. So the address doesn't really, it depends on the chip that you buy. It depends on the hardware. Some of them would go with up to 16 bits, right? The small microcontroller, things that go into your refrigerator, things that we go into a car might have 16-bit address because those are simple processor. Things that go into your computer these days 64 bits. So because it is actually handling a really complex computational task, right? The second question is, for instance, if tag A matches, but information inside is not the data we're looking for, that's not possible. That's not possible. So let me go back to this example, right? The reason why I said that's not possible is if the tag match, what does it mean? If the tag match, it means that these parts of the address are the same. So are you with me so far? If my tag match, in this case, tag, let's say it's tag A, right? Let's say it's tag A. It means that that part of my address are the same. Are you all with me so far? Then the set bit match, the index bit also match. So this part is also the same, right? That part of my address is definitely has to be the same. All right. Are you with me so far? Or okay, let me explain why. Why? If the tag match, and that's good enough. If the tag match, the part that has the tag has to be the same bits. Because we go to the same set, in this case, set number 6, right? Are you with me so far? Basically, we go to set number 6. Definitely, the set bit also will match. By default, that's why we go to set number 6. Anything that go into set number 6, those tags, the set bit has to be 6 as well. So this part of the address are the same, this part of the address are the same. What does that leave us? It basically leaves us with the fact that the data is somewhere in this cache block. It's just a matter of which byte are you accessing. But because the tag match, the set match, that's basically our data might be here, but definitely within that range, within this range for sure, because the rest of the address matched. All right, definitely that's my cache block. Is it more clear now? So it's not connected in that sense, right? But the fact that we go to the same set, it means we have the same index bits. The reason why we tried, so and let me ask you this question, right? I can make the tag bigger for sure. I can make the tag bigger. I can include the index as a part of my tag, right? That would definitely mean that if the tag and the index match, that's the cache block I'm searching. All right. But the fact that we go to set number 6 is already by default, we can cut the index bit out. We don't need that because we already use it. The fact that we go to set number 6, index bit have to match. I just need to make sure the tag match to make sure that my data is already a part of the set, right? So the point that we try to find the information inside, that's the data that belongs to you. The only information left that you have to compare is the tag. The rest, we already took that from the set bit. Is that hopefully more clear? Trying to make sure it's a better way to explain this. So think about it. Let's say you use a set bit as like you go into the movie theater, right? The set bit is the row of the seat that you want to search, and the tag is the number of the seat you want to go into in order to sit, right? In order to sit. You can just once you found the set, basically once you found the set, you know that hey, definitely my data is somewhere on that row. The only thing I have to compare is the number of seats, and that's it. That's why you only just use the tag, and that's good enough because you can find your seat. All right. So that's the analogy that I guess I would compare to. And that's good enough. Why don't I in the ticket, right? In the movie ticket, they'll have a printout that say row something, maybe row N seat 12, right? Why don't you just print row N seat 12N? It's just repetitive information, right? So it's okay to be there because you already said it's row N. So the seat 12 is fine. You don't need 12N on onto that as well because you already filtered it's gonna be row N. The same logic applies here. Everything you store because you need to store the tag in the cache. You need to maintain that tag information. So you don't want to make it big, right? The smaller you can go, the better in terms of the cost. Right? You don't need to store those extra bits. All right, so let's go back to set associativity. The concept is basically has n cache block per set. So let's say you have n-way set associative cache, you can actually go to like Intel and AMD processor and check this out. They'll tell you what's the set associativity of each processor, right? Each processor comes with different configuration. N-way basically means that you have n blocks per set, n blocks per set. And this is actually great. The concept of set associative cache is great. The only downside is once you know what set do you go to, you need to now compare the tag to see which one is your data, right? So let me talk about the scenario where you have a lot of cache block in a set, right? Let's say 16 cache block per set versus 4 cache block per set. Which one is simpler to search and see if your data is there or not? Which one is faster? Diving into 16 items and see which one is yours, or diving into 4 items? 4 is better in terms of the simplicity, right? Because it's fewer things, you don't have to compare to a lot of different things. That's why there has to be a balance between, do we maintain 16 cache block per set versus 4? That also has to do with how long it would take to access the cache. So the smaller cache that are in the L1 cache on your processor typically is like 4-way or 8 ways. At the bigger level cache like L2 or L3, you can go more set associated with it. It can be like 16 or 32. All right, so that's basically uh, how we can design chips. So now we talk about the lookup, the tag, and how does it work. The next thing we have to talk about, let's say I have a situation where you have 4 sets, right? Well, actually, poorly drawn box. 4 sets like this. All right, now it's equal size, hopefully. Set 0, set 1, set 2, and set 3. And let's say each set has 4 cache block. This is way 1, way 2, way 3, and way number 4. Way is like that set associativity, like n-way cache. This is a 4-way cache, means that I can have way number 1, 2, 3, and 4. And if you look at set number 3 right now, there's cache block A, B, and C, and D in here. And I search for address to cache block E to set 3. Are there problems here? I have access to E. What's the problem we have to figure out? It's a myth for sure, right? We will get the data from DRAM. What else? Once we have data, it's full, right? So what should we do? It should kick out somebody, right? It should kick out somebody. Why? How many of you write a program this way? For I equals 0, I is less than n, I plus plus, and then you do something like a of I. A program that follows this way to access data. How common is that? Remember our exam question dot product. Do you write a program something like this? You go through elements in your vector and you would multiply them. Is this a common thing? So what does it have to do with? So let me draw two things that are going on here. If you look at variable, what does PowerPoint refuse to write something on the bottom left? I have no idea. variable I and n. What can we tell about the way we use I and n versus the array A? What can we tell about I and n? How many times do we use I and n actually in this loop? Do we use it a lot? Yeah, it will be used actually n times. So we use a lot. This is called temporal locality. Temporal locality means that if I use a data, if I use something, I am likely to use that same thing again. This is called temporal locality, right? Temporal locality. And we write a program this way a lot. The array A, how do we access array A? How do we access array A? Which one get accessed first? And followed by what? I'm gonna do A of 0, right? I would access A0, then A1, right? Then A2, right? Blah, blah, blah. So let's say I have a 32-byte cache block. 32-byte cache block. Let's say I have a 32-byte cache block. And the array A, each element of A is 4 bytes. So when I access A0, what else am I gonna get in the cache block? Let's say I access A0, and A0 is only the first 4 bytes of my cache block. Which are the other things that I'm gonna have right now in my cache? My cache block is 32 bytes. A0 is the first 4 bytes. What's the next 4 bytes in my cache? In the cache block? It's going to be A1, right? And it's going to be A2 for the next byte, A3 for the next byte. So if you look at the cache block, right, this is A0, and you're going to get A1, A2, blah, 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 up to A7. So if you go and get A0, that's a cache miss. But because the way you access the cache is A0, A1, A2, A3, A4, A5, blah, 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 right? What you get is you're going to have A0 to A7 all at the same time, right? All at the same time. So over here, right, when you fetch for A0, you get A0 to A7. So you have how many cache miss? How many cache miss do you have versus number of cache hits? The way you access the array this way. So the first access to A0, that's a miss because I never seen this address before. For sure, I never seen this before. It's going to be a cache miss because I would have to bring it in. But then when I access to A1, is that a hit or is that a miss? It's a hit, right? It's going to be miss, hit until A7. And then when I go to A8, miss, A9, hit, right? This behavior is called spatial locality. It's called spatial locality. Space, which is the area, right? When you go get one access, it's likely when you write a program that you're gonna access something close by. And when the program, the way you write a program is going to exhibit this behavior all the time. You access something, you're going to need the data close by. That's spatial locality. Temporal locality is the way I would memorize this is temporal is time. I access something, I'm gonna get that same thing again, hopefully in the future. That's more probability, higher probability that I'm gonna access the same thing over again. Spatial locality is if I access something, it's likely that I need something around it, something close by. So the cache, the way I insert and the way I kick things out, should I do something that has to take advantage of these two patterns, temporal and spatial locality? Because when I have set 3 full like this, right? I have new block to E. What do I have to do? I have to kick something out, right? As we said earlier, we need to pick what to kick out. So that's called eviction. The question we are trying to ask right now is, how do we insert and how do we replace the data, right? For a direct map cache where you only have one cache block, that is simple because it's only one cache block per set. You have new data. What should you do? So with the direct map cache, right, there's only one block in a set. You have data that are new coming in. What should you do? Yeah, kick the old one, right? So the direct map cache is simple. New data come in, kick the old one out. For the set associative cache, now there's a playground, right? Well, you have multiple cache block. Which one should we pick? So these are the key issues that people in hardware that are working on caching, right? We actually look into how do we make a policy for this. And today I will talk about what should you assume when you write a program and how does it work in a real processor, right? These are called replacement policy. Well, actually there are three things. Insertion. What do you do when you put things in? Promotion, when you have a cache hit, do you do something with the cache block? Eviction is how do we kick things out? And these three things kind of play together, right? The point is, which one should we kick when you brought new things in? That's called the replacement policy. Replacement policy, as the name suggests, is a policy that we use to determine which block get replaced, right? So when the cache is full, you need to find something to kick. And when you kick it out, it's gone, but you can replace it with a new data. This is called, again, cache replacement policy. So can someone come up with a policy here? What should some of the policy be? I mean, there are multiple options, right? And there's no, well, to be honest, there's no wrong answer. There are, well, I mean, there can be better answer and worse answer, but there are multiple options. Can I pick things randomly? Oh, actually, now you got to the best one of the best ones, actually. So one of the suggestions on the chat is kick the ones that I haven't used in a while. Is that what you're trying to say here? Kick out the one that I haven't used in a long time. So that's what in your processor. So if you buy something from a computer store like Intel chip, AMD chip, they are trying to design to imitate this policy that you suggest. Kick the one that I haven't used for the longest time. Can you tell me why do you think that's the best policy? Which is actually is one of the really good policy. So why is that good? Why is that good? Why is that maybe better than say first in, first out? Exactly, right? Because what you said is because it hasn't been used in a while, it's likely that I am done using that data, right? It's likely not important anymore. And that's true, right? That's true. In most program, the way you write a program is basically follow this pattern. Again, right, these are design choices. You can do pick randomly, right? You can randomly pick. first in, first out. This is basically what I'm gonna ask you to do for assignment 4. Why do we do this policy rather than the one you suggest, which is kick the one that you haven't used in a while? First in, first out is simple. It's actually simple to implement on the C code. What you just suggest is called LRU. This is basically kick the one that you have not used for a long time. This is basically when you buy a processor, assume that that's the LRU policy. It's used everywhere. It's actually used everywhere. You can do not most recently used. You can do least frequently used. Now you look at the frequency of usage. You can use a hybrid policy. The question here is, how do we make something that's close to optimal, right? How can we pick the one that's better? And since we already suggested the one that kind of by default understood as the best policy, the least recently used one, right? Why is this good? This is because the least recently used take advantage of both temporal and spatial locality. If I have access to my cache block, right? If I have access to my cache block, those are not going to be the least recently used. Whenever I have an access, when you have an access, I will call this most recently used, like most recently used. So I'm gonna protect that because I think I will use it again. The benefit is this is likely to be effective, right? This is likely to be effective. So let's say I have a cache access by time, right? So if you look at the timeline, this is time. I have access to A followed by B followed by C and D right here. And then I have access to E, and let's say you can only hold 4 cache block. Let's say you can only hold 4 cache block. When E comes in, which one do I kick out? Which one do I kick out? In this case, if I use LRU or least recently used, this is called LRU. A, right? You're gonna kick this out, replace this with E, right? So that's how it works. And this is likely to be effective. What are the downsides? So I mentioned that most processors would try to imitate this. The reason why I mentioned the word try to imitate this is basically a little bit out of the scope of what you're supposed to know, but I want to tell you because I do have more information about in the real process of how it's done. The downside of this is if you want to implement this policy in hardware, what do you have to do to be able to pick out the least recently used? Do you need something of an order of which one come in first, which one get used when? Do you need that? But you do have to have a way to pick which one hasn't been used the longest, right? So this is what you need, right? So you need to pick the one that have not been used the longest. Actually, wow. So on the chat, there's a policy you suggest, increase the time, like increase the counter every time you have new access, right? Is this what you're trying to say? Like, I maintain the way to count the time, and when I have new access, I increment the time, and you pick. You just came up with the actual, there's a paper in 2010 that talk about this. So there was a paper from Intel in 2010 that talked about the policy close to what you just suggest. That in order to do this in hardware, I mean, back in the day, we would say, hey, we need to sort, right? We need to sort based on the time of access. And whenever I access another block, I need to sort them, right? And then that Intel paper say, hey, but I mean, what you need to do is just some ordering, right? We need some way to order them, and we can use counter for that and count up when you have new access for blocks that you are not accessing. That way, the number would represent how long haven't used that one. So if you want to talk about more detail about that, I would be more than happy to talk about the content of how that is implemented. But here's what I want to get from this slide. So basically now let's come back to the content of the class. By the way, I am more than happy. Actually, I'm glad that you suggest that solution because it's awesome. It's actually how we like the current proposal on the effective way to implement LIU in hardware, right? Which is awesome. How in reality, when you buy a chip, one thing you can assume is it's going to be LIU because the way Intel and AMD and Apple ship, right? The way we implement the cache is going to closely resemble this policy. How you implement this in hardware, it depends. There has been paper, as I mentioned already that use counter. Some of them would use a variation of this. It's not exactly LIU, but it's approximate LIU, right? LIU is kind of costly to do in hardware. But if you look at things like web cache or database cache, LIU is perfect. Why? Because you don't have to sort in hardware anymore, right? You don't have to do sorting in hardware. So you can write a program to figure out which one do you cache, which one do you throw away. All right. So that's why we want to make sure you understand the concept behind LIU. Okay. So awesome. I'm actually glad that this has been suggested. So the problem with LIU is great. LIU is great, but there's also a possibility that I can destroy. I can destroy LIU. How can I destroy the LIU policy? So let's say I bought a processing chip. I write a program, and by accident, I make the cache hit rate really low. How can I do that? Again, you can map many data to the same set, right? As long as this is basically have multiple access where my address has the same index bits, right? If I have the same index bit, what does it mean? I have the same index bit, but different tag. What does it mean? Yeah, they'll go to the same set. So let's say I have a four-way cache. Let's say I have a four-way cache. I go through the address. Sorry, someone call me. So let me pick up the phone quickly. Sorry, huh? All right. Sorry, this package coming. So let's say we have a four-way cache, right? And my code goes through A, B, C, D, E. The tag A, tag B, tag C, tag D, and tag E, they happen to go to the same set as we have been developing so far. So this is the content, right, of my cache here. We have four-way cache. We can hold up to 4 cache block, right? I have access to A, then B, then C, then B, and then E. And so basically this is what I do. A, B, C, D, E, and then repeat the same thing again, back to A, B, C, D, E. So what happened when I have access to E? Which one do I kick out? A, right? I'm gonna kick out A, replace it with E. So then the next access is what? What do I access next? I'm gonna access A again, right? So when I have access to A, is that a hit or is that a miss? It's a miss, right? So you're gonna kick out B, replace it with A, and then you have access to B. Miss again because B just got kicked out. And when B comes in, you kick out C, replace it with B, right? And then you have access to C, which you would kick out D, have access to C. Do we ever get a cache hit in here? Nope, right? So this is one thing that can happen. Happen by accident because you go to the same cache, right? So, great question. So there was a question on the chat that say, hey, when this happened, does this impact security? So this would what I'm gonna say is it doesn't really impact security, but impact performance, right? I can write a program this way. So let me create a program that when I run it, the first step is I look at the cache configuration of my machine. I can totally do that. That's a command that I can do to check the cache configuration inside C. The second thing I do is write access to cause thrashing. So when I do this, when I run this program, what's gonna happen to everything else that is running on your computer? What's that likely to happen when I run this program along with something else on a computer? So will the other program see the effects? Will they see the slowdown by the program? Right? So because I am running a program that kind of destroy any cache locally, I'm gonna kick everything out from the cache. Your friend that are running the program in parallel on a different processor might be like seeing a lot more cache miss. So is this a security problem? It's not the case where you're gonna see the problem where someone look at your data, but this is more like a performance problem. We call it interference. Interference means that I'm running my program, but because I'm running it with another program, it's actually a lot slower. Because another program is trying to kill my performance because the way they use the cache. Right? So is it more clear? Now, I mean, with this explanation, is it more clear that I can totally write a program and it would run and would kind of destroy the other program's performance? So actually, this is one of the big problem in cloud infrastructure. How do you prevent something from happening? How do you prevent something like this from causing slowdown, right, of another program? If you're interested in this, definitely let me know. I am actually looking into this. Like part of my thesis is looking into this problem as well, but it's not like right now. It's not the time to talk about this question. It's a little bit too advanced because many things can go on. One of the like what I just explained it to you is one example of what can go wrong, right? The point here, right? My point here is you might not even maliciously, but by accident, right? By accident, you can write a program that totally exhibit this behavior by accident because you map your address to the same set bits. That's it. Kill the other program performance. It can happen. So that's a set thrashing problem. The other the different design things is called insertion policy. Because when you have a cache miss, what would happen is you go to DRAM, right, to get your data. That's where you store the data. The DRAM say, hey, here's your data, send it back to the cache. So you would put the data in the cache, right? Something like this. You have cache in the cache, you have A, B, C, D, and E, right? And you have access to E, this is in DRAM. DRAM say, hey, here's E. Then you put this in the cache, and then most of the time, in the processor that you buy, this block E is going to be marked as most recently used. Why is that? I'm going to make sure E is most recently used. Why is that? I mean, it's actually self-explanatory, but I want to make sure that point is clear. Because you just access it, right? Because you just use it. So that's why we would mark E as the most recently used. All right. So because we just use E, now we mark them as most recently used, we decrease the chance that E get kicked out because we just use them. So insertion policy, we can use a different policy as well. Right now, by default, just assume that when you have access, you insert into the MIU or most recently used position. Promotion goes the same way as insertion, but the only difference is promotion is not new data coming in. This is when you have a cache hit, right? So when the cache block is accessed, let's say this is your set, say set 7, some random number. We have cache A, B, C, and D. And you just access cache block C in here. You have access, yay, right? So C would get promoted to most recently used. So that's the cache promotion policy. You would promote them into the most recently used position. And this can be done by updating the bits that say, hey, this is now the most recently used. The other guy would become not most recently used. All right. So this is basically governing how do we pick which one go into the cache and which one get kicked out. All right, we are done in terms of like managing the block in the set. To wrap it up, we can categorize the types of cache miss into 3 different bins. The first bin is called compulsory miss. This should be, well, once you know the explanation, it should be pretty self-explanatory. Compulsory miss is compulsory. What does compulsory mean? Can someone write in what does compulsory mean? I'm gonna go and get my package really quickly. I'll be right back. So compulsory means you must do it. You must run into a miss. Why? Well, the first time you see this data, it's the first time you see this cache block. So there's no way that cache block would be in the cache. That's why we call this compulsory miss. The one thing that you can do to avoid this that is done in many modern libraries and many scientific computing applications, we can do a technique called prefetching. In case you see this in the future, what does prefetching do? Prefetching means I'm going to go and get that data ahead of time before I actually need them. So this is a technique that's actually used quite a lot and in modern application. That can help with compulsory miss. Conflict miss. What does conflict mean? Conflict means there's like fighting going on or some disagreement. This basically is the case where you have a lot of data mapped to the same set. A lot of data mapped to the same set. So even though the cache is not full, there's a bunch of data going to set 7, for example, right? A bunch of data go in here. You are going to have conflict miss because you are running out of room in set 7. The last type is called capacity miss. That's when the cache is too small. That's when the cache is too small to cache everything. So in this case, you just need to make sure you either do a better management, or you can come up with a better technology to increase the cache size. Right? You can also increase the cache size with new technology as well. One of the, well, actually, this is actually done in modern day computer. When you look at the different generation of processor, you will see that the size of your cache actually grow up and up and up and up. If you look at the server processor, for example, the one that AMD just launched last week, the size of the cache is actually go beyond 500 megabytes. That's a lot, right? So now you have a lot more room that you can cache the data, right? And why do we need them? Why do we need more cache? Why do we benefit from more cache? It's about performance. It's about how fast does your program run, right? So to measure the performance of your system, one thing that you can look into is what's the cache hit rate for all my memory access? How often do I hit in a cache and how often do I miss in a cache? What's the cost of each hit and miss, right? You can have a cache that are really fast, and you can have a cache that are bigger but slower, right? So what's the cost of each hit and what's the cost of each miss? And what's the total cost when you have a data load? What's the total amount of time required for me to get my data? And I'm gonna use the example to show the trade-off here. So let's go to the first example, right? The first example. Let's say I write a program in a computer that takes 2 cycles for the L1 cache, 5 cycles for the L2 cache, and 25 for DRAM. And my program access 100 different pieces of data, and it has 80% cache hits for the L1 and 80% cache hit for the L2. How many cycles does this take? So let me do this quickly, right? This is L1, L2, and DRAM. Number of access. So how many access go to L1? I have 100 loads, right? So all of them have to go to L1 to check, hey, is my data over there? With me so far, I have all 100 going to L1 to check, hey, is my data there? For those that are missed in the cache, in the L1 cache, how many go to L2? How many miss in the L1 cache? I have 80% hit rate, so 20 go into L2. Then how many go to DRAM? This would determine whether you need coffee or not, actually. What's 80% of 20? 4, yes, thank you. So for all the 100 requests that go to L1, this is the time it takes, right? 200 cycles here, right? 200. For the L2, you have 20 of them. Each one of them take 5, so that's 100 cycles. And then 4 of them go to DRAM. Each one of them is 25 cycles, so in total it's 100 cycles right here. All right. With this, in total, we spend 400 cycles. Now let me rewrite the program, and hopefully I make this more efficient. I can somehow magically improve this into 95%. I improved the L1 hit rate to 95%. So let's do this case right here. Number of access and the time it takes, right? L1, L2, and DRAM. So all of 100 will go to L1 by default. That would take 200 cycles. How many go to L2 with 95% cache hit? So only 5 go to L2, and how many go to DRAM? Was 20% of 5. 1, right? So this will take 25 cycles. It will take 25 cycles. So in total, you are getting faster. It's only spending 5 to 50 cycles to get out this load. Is this faster? is quite a lot faster, right? It actually about like, well, the speed up is 400 over 250. I don't want to do division, but it's actually really it's much faster. So there's a question on the chat that say, what condition will we go to DRAM? The condition that go to DRAM is you have to miss in every single level of the cache. So let's say you have 3 levels of caching, right? You have CPU, you have L1, L2, L3, DRAM. Let's say this processor kind of looks like this. You check L1, and it's miss in L1, check L2, miss again, check L3, miss again. That's when you check DRAM. All right, so hopefully that's more clear with why and what condition will I have to go to DRAM. All right, so with this, right, if I can improve the hit rate, I can make my program faster. So let's go through the second example. Same setup for my computer. I try to implement a mechanism that has a really high L1 hit rate, but notice that I somehow increased the number of memory access from 100 to 1000. Is this faster or slower? Can someone tell me, is this faster or slow? It's going to be slower, right? Because by default, that 1000 load will spend 2000 cycles for sure in L1 alone, right? So that alone is going to make things much slower. How about the other example? Same configuration again, really kind of bad in terms of the L1 and L2 hit rate, but I can reduce the number of loads from 100 to 10. Is this faster or slower? It's actually faster. If I do the math right, it is actually faster, right? So if you look at the program performance, there are multiple things that involve, right, in making the program either fast or slow. One thing you want to do is to reduce the miss rate. For example, how do you do this? For example, when you loop over a large range of data, cut it, divide and conquer. Basically, you now can loop over smaller size and cut it up into chunks. That way you go into the cache all the time. And then you go to the next part of the loop. All right, that's one thing you can do. These are whatever this is actually will be in PCSA in more detail. The next class after this, basically after this course, and this is a part of lab 3 in PCSA. We'll ask you to improve the performance of a program by applying multiple tricks, and one of the tricks that you can do is to improve the miss rate. The second thing you can do is to reduce the number of memory access. Basically, make sure your program has to go to the memory fewer times, right? So these tricks are pretty, actually, it's one of the common tricks that we do in algorithm. Basically, reduce the number of memory accesses. So you can design a new algorithm that have to go to the memory fewer times. So these are common in modern day code development. And one thing that you might have now realized, like, okay, this sounds awesome, but I don't want to be aware of this all the time, right? That's kind of annoying. I don't want to be an engineer or computer scientist that go into a job market and every time I write a program, I have to be aware of this caching. It can be annoying. So in modern libraries, these are actually, some of them are done by default, right? So modern libraries can actually squeeze out performance of the computer for you. Programmers in high performance computing community would always try to come up with new APIs, new libraries that you can call, right? So that it try to make sure you make the most use of the cache. My takeaway message is the cache hits can matter for performance. The cache hit can matter for performance. And I know I'm slightly going behind the time I told you we're gonna have like maybe 40 minutes for the Q&A for assignment 3, but let me kind of wrap up with the last thing. If you have writes, right? If you have writes, when a cache block is written to, the data change. So let's say I have L1, right? This is L1, L2, and this is DRAM. And I have the address I right here that are both in L1, L2, and DRAM. When I fetch this data, when I go and get the data, it's originally the value of this is 0. And then I do this, write to I. Can someone give me the number from 0 to 9, just any random number? All right. Well, anything not 0, because we want to write something else. Okay. Write 0, write 6 to I, and then I do again, write 7 to I, right? And then I write 8 to I. What would happen? So when I have this, right? The first write over here, right? This thing changed from 0 to what? 6. So what happened here? What should we do here, actually? I have the first write to 6. It's a cache hit because I have I in the L1 cache. I'm gonna change the data, right? The problem, the issue here is, well, L1 is updated. How about the data in L2 and DRAM? How about the data in L2 and DRAM? What do we have to do? What should we do? Well, if we do nothing, how can we make sure that, let's say I evict the block from L1, what would happen? If I evict CT, I evict I, what would happen? Now it's gone from L1. Yes, we have to somehow save it in the next level so it won't be lost, right? So in your computer, there are two main policy that you can do. The first one is simple. It's called write through. Write through is whenever I update everywhere. So when I have write to 6, when I have write 6 to I, I'm gonna change this. I'm gonna update so that everything is 6. And then I have write 7 to I, right? This thing changed to 7. I update everything to 7. When I have another update to 8, I will change this and put in 8. So is this good? I mean, are we good now? Basically, are we all correct? Let's say I have eviction, I kick out I, it's now gone from L1. We have a correct data, right? Yeah, it does feel like a logic of GitHub because this is how you, I guess, commit the changes as well, right? But this is a little bit wasteful as well, right? Because if I have a, yes, exactly. It's not also long, it also wastes the bandwidth. Because every time you modify something, you have to change every single level of my cache. All right, you have to change every single level of my cache. And now my cat is trying to sabotage this class. So let me ask you this question, right? Let me go back to let me go back in time. And I have 0 here, 0 here, and 6 here for I, right? When I have write 7 to I, can I just do it in the L1? Can I just do it in the L1? Because the next access is gonna go to L1 anyway, right? Can I do that? It's a cache hit, right? So I can go to L1 if the data is there. So if you think about that in this particular problem, when do I have to update? Yeah, you only have to update when you evict, right? You only have to update L2 when you evict from L1. That's when the data is gone. So you make sure you update. Otherwise, you don't need to update. This is called write back policy. This is called the write back policy. And the write back policy will maintain one additional bit. We call this the dirty bits to specify whether we have to update L2 or not. I'm going to show the example here, right? This is L1, this is L2, this is DRAM. You have write 6 to I, write 7 to I, and then write 8 to I, and then you have evict, right? So over here, right, originally, I is 0 everywhere, right? Then you write 6 to I. You write 6 to I. This is what happened. You basically write the value 6 here. 6, right? And because you haven't evict I, well, it stays there. You write 7 to I, and you basically say mark this as dirty. You mark this as dirty. It basically means that if you evict this block, make sure you write the data back to L2. So when you have the future write to 7, you keep writing, right? And then write to 8, you're going to keep writing. Notice how I don't have to update L2 and DRAM. Then when you evict, you check the dirty bit. If the dirty bit is 1, it means that, okay, the lower level cache is not updated. You have to have update this. 8 goes in here, and you also mark this as dirty, so that when you write and evict from L2, then you update DRAM. Basically, this is how the write back policy works. You only write and only update the data when you have the eviction. All right. You only update the data when you have to kick I from L1 to L2. And that's it for today lecture part. Sorry about going a little bit over time than I promised. Before we leave today, there are 2 things I want to mention. There's new in-class exercise 11 that has to do with caching. So we have in-class 10 that are assembly and in-class 11 that are caching. We can talk about this in the Discord session. We also will talk about assignment 3 if you want. Basically, if you're stuck anywhere in assignment 3, let us know so that we can guide you or hint you to how to work through assignment 3. Then I will record a video for the midterm exam recap. I'm going to go through the question. I want to do it in class, and then there was a suggestion on from section 1 that say, hey, I think we better focus on assignment 3, and I can just do the recording for midterm exam recap and put it on YouTube so you can watch it anytime. All right. So this will be a separate thing posted on YouTube. Whenever I'm done, I'm going to let you know that, hey, the recap is over on YouTube. It's up there. You can go to the link to access it. Otherwise, right now, we're going to transition to the Discord session and work on these 3 things in class 10, in class 11, and assignment 3. Yes, exactly. I can definitely do that. Do you want to do it now, like on the WebEx? Let me open it up. Oh, actually, let me open it up on my desktop. So let me unshare this.